it was rather difficult to discern the internal structure of the Milky Way since we're embedded within it. But the first person to do that was not an astronomer. He was actually a landscape gardener. And I know about him because, as often mentioned, I spent a lot of time in Durham, and this is where he lived. And Thomas Wright can be regarded as the first person to realistically, in print, explain the origin of this band of light we see across the sky. And in 1750, he wrote this book, A Theory of the Universe, and this emphasizes that for many years, people thought that the Milky Way was the entire universe. This is the figure. You can see the sun is one star embedded within a disk of stars, and when you look along the plane of that disk, the stars all line up, and they're very, very dense. You won't resolve them necessarily. You see this band of light, whereas if you look at right angles to that disk, you don't see so many stars. And so he grasped the idea. Unfortunately, he hadn't any scientific training. He was so excited by this realization. He went on and he created a divine being at the center of the disk, and the book sort of rambles a bit. But he basically got the clear idea of the origin of the Milky Way. A person who's much more like a modern astronomer was William Herschel. He was originally German, but he moved to the UK, and he built his own telescopes. Here's one of them, and you can see they're pretty large things. He ground his own mirrors out of metal, and he charted the sky for what he called nebulae. He didn't realize what they were, but he cataloged them. And there's this very important sentence in his publication in 1789 that some of these nebulae, most of which are gas clouds within the Milky Way, some of them are actually external to it. And so he first postulated that outside the Milky Way, there might be other galaxies, like our own Milky Way. So the universe would be enormous by comparison to what had been previously imagined. And the first individual to demonstrate that galaxies like this particular spiral, the Andromeda spiral, our nearest neighbor of comparable mass to the Milky Way, is external to it. So the first thing you have to do to determine that a galaxy is outside the Milky Way, of course, is to measure its distance. And what Hubble did was measure the brightness of variable stars. And so this is a plot of the brightness of stars within the Andromeda spiral. And the period of these are stars that were known in the Milky Way. They pulsate in radius. And the period of pulsation is known to correlate, and we understand now physically, with the period and luminosity. So if you know the period, you know the luminosity of the star. If you know the brightness and the true luminosity, hence you can get the distance. And so Hubble transformed our view of the universe by demonstrating that this galaxy was a galaxy very much like the Milky Way outside the Milky Way. Now I'm going to take you to the edge of the universe, and the distances that we're going to cover are much larger than the kind of distances that Hubble covered in his own career. So you can think of an astronomer very much as an archaeologist. When we look at the universe, we're looking back in time. The universe is so vast that the speed of light is finite. And so, for example, when we look at the sun, we see the sun as it was 8 minutes ago. That's the time a light ray takes to reach the Earth from the sun. If we look at the nearest star, we see that star as it was 4 years ago. That's the light travel time from the nearest star to the Earth. But the whole situation transforms dramatically when we use a powerful telescope like the Hubble Space Telescope. My colleagues and I took this image. It's a 2-week exposure with the Hubble Space Telescope taken a few years ago. It's called the Ultra Deep Field. And what you see in this image is galaxies that are seen not a million years ago, not a billion years ago, but over 13 billion years ago. Now, the age of the universe is 13.8 billion years. So what you see in this image is a time tunnel that's looking back 97% of the way back to the Big Bang. And so the challenge is to time slice this image and piece together the history of the universe. Encapsulated in this image from the most distant objects, shown here in which I'll talk about later, to the brighter, more nearby objects, we can try to piece together the evolution of the universe. We can't study the evolution of an individual object. We don't live long enough. But we can try to piece statistically the evolution of the universe directly from looking back in time. So I have to introduce redshift. And so the universe, as you probably know, is expanding. So concentrate on a galaxy here, and it emits a light ray towards the Earth. So we're sitting in this object here. As that light ray travels towards us, space itself has been stretched. It's fallacious to think of the expansion of the universe as galaxies moving as projectiles through empty space. That's not the story at all. The galaxies themselves are actually hardly moving at all. They may have the odd peculiar motion, but they're stationary to all intents and purposes. It's space itself that is being stretched. And as that space is stretched, so this light ray is stretched in wavelength. And if we can measure its wavelength, then not only can we measure how much the universe has expanded since the light ray left that galaxy, which we call the redshift, but we can also estimate the time of the age of the universe at that particular point. It's a complicated idea, I know, but think of redshift as an axis, and the larger the redshift, the earlier in cosmic time you're looking. So a redshift of, say, 1, where the light ray has been stretched by 1 plus 1, so its original wavelength doubled, corresponds to looking about halfway back to the Big Bang. I'm going to talk about redshifts out here when the universe was less than 1 billion years old or so. So what are the tools for doing this? How do we slice the universe in cosmic time? Well, we use the most powerful ground-based telescopes, and the ones my group uses are the twin Keck telescopes, whose mirrors are 10 meters across on the summit of the hopefully extinct volcano on Mauna Kea in Hawaii, and the 4 8-meter telescopes called the Very Large Telescope in the Atacama Desert in Chile. And we place spectrographs on these telescopes. You can see they're monstrosities. They're enormous instruments. They cost about $10 million or so to produce. And there are optical spectrographs and infrared spectrographs. And of course, we use the familiar Hubble Space Telescope, which is launched in 1990, had a rather checkered initial couple of years, but eventually was working very well and is still functioning brilliantly. And I'll talk briefly about the Spitzer Space Telescope and the Planck mission, which studies the microwave background itself. So how would you find a distant object so that you could start peering back to when the universe was very young? Now, you might think the brightest object is the nearest one, and the faintest object is the most distant. Galaxies have a huge range of luminosities. There are feeble ones and bright ones, just like stars. And so you've got to be a little bit more clever. And so fortunately, there's a trick, which was first introduced by one of my colleagues at Caltech, Chuck Steidel. And the idea is that hydrogen cuts out the spectrum of a galaxy by absorption. So the universe is actually completely full of hydrogen. It's the most common element, of course. And it's not only in galaxies, but it's in deep space as well. And so as a light ray comes from a distant galaxy, it can be occulted by this hydrogen. And it occurs at a specific frequency, which we call the Lyman break, named after a particular series in the hydrogen spectrum. And what you see is this galaxy, if you study it in the red filter, the green filter, and the ultraviolet, unlike all the other galaxies, this galaxy is absorbed. You can see it in this picture here, it's in this picture here, but it's not in this image here, whereas the other galaxies clearly are. So this tells us that this galaxy in particular is very much further away than all of these other galaxies. And this technique can be extended out with a number of filters on the Hubble Space Telescope. So this is wavelength, so here's the infrared, here's the optical, and here's a spectrum of the galaxy. It'll run through again. And as you can see, as it gets further away from us, as the redshift increases and we look further back in time, this galaxy disappears progressively to the longer filters. So we're harnessing the expansion of the universe to directly slice the universe in cosmic time. So what have we learned? Well, we've learned that we can see that evolution directly. So here are two galaxies that are very representative of the galaxies we see in the universe today. This one is obviously a spiral galaxy, very similar in form to the Milky Way, except it has a companion. This galaxy is what we call an elliptical galaxy. It has no spiral arms. It's simply a ball of stars. The origin of these two different classes of galaxies is itself a very important question in astronomy. If we go back to when the universe was 5 billion years old, so that's about 40% of its present age, you can see the galaxies, and these are Hubble pictures, you can see this galaxy bears some resemblance to a spiral galaxy. It looks a lot less mature. These two galaxies do resemble an elliptical galaxy. But there are galaxies that are irregular, and we do see those in the local universe, but not with the abundance that we see at this early time. So one can see that there's some sort of maturing of the population over this period of cosmic history. But if one goes back to when the universe is only 1 billion years old, these galaxies don't resemble anything like what we see today. They're physically much smaller. These figures are all scaled so that the physical sizes are comparable over cosmic time. Many of them have multiple images as if they're coalescing and growing. And so they're baby galaxies that are assembling by merging with their counterparts. So over the time of my career, this is a plot of the most distant published object as a function of publication date. So often mentioned when I was an undergraduate here in the 1960s, the most distant object was known as a quasar. This is a luminous galaxy with a very intense black hole in the center. Normal galaxies were hardly seen beyond a redshift of 0.3 or so. So really, we were still in the local universe. But when Steidel and others and the big telescopes came on in the 1990s, you can see suddenly we started probing periods when the universe was only 1 billion years old. And in the last 5 years or so, you can see the current frontier takes us to when the universe was only 500 million years old or so. So this is a very exciting time. You can see the progress in the last 5 years or so is extremely rapid. So what's the quest? Why are we interested in finding these very early galaxies? Well, here's a theoretical picture. It's an unfortunate fact. We live in a world with theorists. They have no need for observations. They have everything sewn up. Here's the glow from the Big Bang, what we call the microwave background. And when the universe was expanding for the first time, 370,000 years after the Big Bang, the universe was cooling, and the hydrogen atom formed for the first time. And we see this dark hydrogen clouds, no starlight, no galaxies, but these dark hydrogen clouds eventually collapse under their own gravity, and they ignite nuclear fusion in the birth of stars. So we call that moment cosmic dawn. We've no idea exactly whether it was a dramatic moment or whether it was a gradual process, as seems to be illustrated here. These stars have no heavy elements. So everything that you see in this room, the metals, the stuff that makes up our bodies, was produced and synthesized in nuclear reactions in stars. The Big Bang only produced hydrogen, helium, and a few very light elements. So these stars are very hot compared to stars in the Milky Way that have these heavier elements. So they produce a large amount of hot radiation, which produces these ionized bubbles. So that poor hydrogen atom, which only formed 370,000 years, is now broken apart into its electron and its proton. And presumably, as more of these bubbles form and expand, the universe transforms from being a dark hydrogen to being a fully ionized gas. And here's an evidence of how the theorists have it all sewn up. This is a numerical simulation of this reionization process. The expansion of the universe has been very conveniently taken out in this slot box of space that is rotating. The ionized regions around the young galaxies are shown in these blue regions. And as time progresses, they grow and they connect, rather like Swiss cheese. And over cosmic time, the universe transforms from being dark and full of neutral hydrogen to being one that's fully ionized. It is rather a tediously slow movie, but this is 300 million years, so be grateful that they have actually sped it up for you. Okay, so this is work done at Stanford by Tom A. Bell and his collaborators. So you might think that the way to find the birth of galaxies, which after all, if you think about it, stars are the fuel that makes up everything that we see, so it is, in a sense, our own origins. Finding the birth of starlight is perhaps just as an important milestone in civilization as understanding the origin of the universe itself. So finding this moment of cosmic dawn is the quest of our ERC grant. And you might think that the most profitable route is to look for stars which don't have heavy elements. After all, the first generation of stars that are formed immediately in this early period won't have any of the elements like calcium, magnesium, oxygen, and iron. As these stars evolve, the more massive ones explode at the end of their lives, and they produce supernovae. And a supernova is an exploding star that propels this nuclear product back into space. And so, you're looking for this window in time when the stars are formed, but the supernova haven't yet exploded. And simulations suggest that this is a very short period of time. It's about 50 million years. Now, I know 50 million years is not something you'd want to wait yourself, but compared to 13.8 billion years, it's a very, very narrow time interval. So it's a needle in a haystack. To find such objects that are chemically pristine is going to be very, very hard because they will be very, very rare. So a more interesting question is, when did this hydrogen ionization begin? And this is where this Planck mission comes in. So I told you the glow from the Big Bang, it's a thermal glow, it's the heat of the Big Bang. It was detected in 1965, and is now studied in great detail by this Planck satellite. And this radiation is polarized, and it's polarized by scattering by the very electrons that are in deep space. So this is the furthest that we can possibly look back at the moment. You're looking at a surface here that's when the universe was only a few 100,000 years old, and you're seeing the beginnings of the structures that lead to the galaxies that we see today. And as that light travels towards us, it passes through this column of electrons which were formed when the hydrogen was ionized, all the way from the beginning of reionization to the present day. And so the Planck team, and I'm not a member of the Planck team, claim that this reionization began when the universe was 500 million years old and ended when it was 1 billion years old. And if we go back to the frontier, you can see that we're probing this period already. And so that's very exciting that we have the possibility of studying objects in this important interval. So how do we know that the Planck team are correct? We have two ways of testing that they seem to have got the right answer. One is that we can probe the space in between galaxies by shining a luminous object through that medium. So think of a quasar, which is a very luminous galaxy, and the light from that quasar passes through deep space. And it looks for these ionized bubbles that I showed you earlier. And where there's ionization, the hydrogen absorption is reduced, and you see these spikes. And where the hydrogen is neutral, that is in its atomic form, the absorption is complete, and we see darkness. And so we would expect, as we go back in time to earlier times, we would expect to see more darkness. We would expect to see more neutral hydrogen. So one of my postdocs, Sarah Brosman, who recently finished her thesis at Cambridge, compiled the most comprehensive list of quasars, 62 of them, and here are 7 of them. And you can see these are the spectra of the individual quasars. This is the quasar light, and here is the absorption by the clouds of hydrogen. And you can see it's almost complete darkness as one goes to the higher redshifts. And so this is the first indication that something is transforming the universe at this early time, corresponding to when it was about 500 million years old. The other technique that my colleagues and I used in California was looking for emission from the galaxies. And this hydrogen line of Lyman alpha is a line that's produced. It's the most common line of hydrogen. It's normally in the ultraviolet. And it's scattered by the neutral hydrogen. So even if you haven't done any atomic physics, let me explain how this would work. So the darkness of neutral hydrogen is really acting like a fog. So as you look back in time to greater and greater distances, think of every automobile on this motorway as a galaxy, and the glowing headlight is this Lyman alpha line. We would expect, as we enter this fog, which scatters this line, that the visibility of this line would start to decrease. So two of my students and I began to do this project. It took several years, as you can see, using the Keck telescopes. The first student, Dan Stark, is now a professor at the University of Arizona. Matt Schenker, the second student, decided to go to Wall Street and earn a lot of money, and we will definitely keep our eyes on him if he wishes later to help us with a donation. And we did this big survey of hundreds of galaxies out to the highest redshifts that we could possibly do, which is, of course, very difficult, even with these very, very powerful telescopes. Now, let me tell you, I'm very old-fashioned. I love going to the telescope. When I started observing, of course, one had to go to the telescope because there was no internet. But now there's very fast internet. It is, in principle, possible to observe remotely. I could, in principle, observe in Hawaii from my office at UCL. But I'm very old-fashioned. I like to go to the telescope for two reasons. One, I find that I focus on my research, especially if I go with my students. And there's nothing like the excitement of making a discovery in real time at the telescope. And this frequently occurs. You can see Dan Stark, when he was a student, he got amazing coverage. He was on the front cover of Time magazine, which was quite an achievement. Here's another of my students in his pajamas, it seems, controlling one of the biggest telescopes in the world. And this is the inspiration, I think, for their careers. And it was very much for mine when I was at UCL as well. Now, there is one disadvantage of going to the telescope and flying all the way to Hawaii: cloudy nights. So, you know, you're scheduled a particular window of time, and there's no guarantee that the night is clear. This is a cloudy night photograph. This guy here has just finished his thesis. He's very happy. He doesn't have to worry. He's Italian. They're always happy. I mean, just you know, this guy here, his thesis is rapidly going down the drain. You know, he's very, very worried. He's lost 4 nights to cloud. So my job as professor is to buy the pizza and the wine and try to cheer everybody up. And I think that's why this photograph is slightly blurred. Okay. So anyway, we found after this effort that the fraction of galaxies that show this line does indeed drop remarkably as one goes to earlier times. And so we're entering the reionisation era, when the universe started to become neutral at this period, redshift 7 to 9. So can you probe deeper? Well, I showed you this deep image from Hubble. And this was taken in 2012. It was a collaboration with a group in Edinburgh. And here we are outside the Royal Observatory in Edinburgh. And we found 7 objects out to redshifts of 10 or so, or 11.9 maybe. And we found 75 objects between a redshift of 6 and 9. And so this gave us our first census of how many galaxies there are as one goes back to even earlier times. Now, there is another technique, and I'm just going to illustrate this quickly. It's called gravitational lensing. So the idea here is that if you look through a foreground cluster of galaxies, which has a huge mass of dark matter, it acts like a sort of telephoto lens, focusing the light from a background object and magnifying it. So it's like making your telescope 10 or 20 times more powerful. this trick only works by looking in the direction of one of these clusters. It's a feature of Einstein's theory. So Einstein predicted that the gravitational force is transmitted over distance, not by some magic, as Newton worried greatly about this, but the distortion of space-time itself. So the reason the Earth orbits the sun and knows about the presence of the sun is that space is distorted around the sun and the Earth is following a trajectory in space-time that is the result of the mass of the sun deflecting space-time. And, you know, Einstein predicted that this deflection should be seen at an eclipse, and that the stars would not be in the same place at the time of the eclipse as when the sun wasn't in the way. And next year is the 100th anniversary of this event, where this gentleman, Arthur Eddington from Cambridge, a hero of mine because he was a theorist, but he's so excited about this, overnight he became an observer. And he went to Africa, made measurements, and you know, probably this verification was the most important reason why Einstein became famous overnight. And in fact, Eddington, you know, was queried by journalists who asked him, Professor Eddington, apparently there are only 3 people in the world who understands Einstein's theory, to which Eddington apparently said, who's the third person? So clearly an amusing and somewhat self-confident guy. Okay, so how does it work? Well, here's a background object. Here's the lens, the cluster of galaxies. And if the alignment is very good, then you can see multiple images. You see the light of this galaxy by more than one route, very much like a mirage. Even offset, there's a small distortion. And further away, space is slightly stretched and distorted by mass wherever you look. So another movie, here's a transparent lens that's just sort of simulated through one of these deep Hubble images. And you can see, you can get everything from rings to highly distorted objects. But even far away, you know, the images are very slightly distorted. I got very excited about this 20 years ago, or maybe it's more than that now. And with a student at Durham, Ian Smale, we found these multiple images in the Hubble data. Here's 1, 2, 3 images of the same galaxy viewed by different routes by this foreground cluster. So these objects are all, these images are further away than this. And so state of the art today is this particular cluster has 180 multiple images. So it's truly revolutionized the way we use these telescopes. And so, so here are the pioneers in 1988, Geneviève Soucaille and Yannick Mellier at Toulouse, and here's a young Richard Ellis before he endured being head of department. And you can see the most distant objects selected by this technique, and the ones in red correspond to ones with my collaborators, all the way out now to redshifts of 9. So these 2 techniques, pointing Hubble for a long time in a direction of sky and using these lenses, give a consistent view of the decline of galaxies out to when the universe was about 300 million years old. And so it's looking like cosmic dawn. You know, we're approaching it. This is about as far away as we can look at the moment, redshift 10 or so. We have this one object that we found earlier this year. We're published in Nature with our Japanese colleagues and 2 of my fellow workers here at UCL at a redshift of 9.1. Here we are. Here's Guido Robert Spersani is a graduate student here. Here's Nicholas Laporte, a postdoc at Paranal. Here are the mighty 4 8-meter telescopes. It really is a religious experience to go to this observatory. And we detect the redshift of this object, and it has old stars. And so this is where the Spitzer telescope tells us these stars are old, and this galaxy is already mature at this very early time. So if we can get an age of this object, we push to when the universe tells us when starlight first switched on. And it looks like it's about 250 million years after the Big Bang. This is our first glimpse of when cosmic dawn might have occurred. So I'll just finish with one other probe, and that's this remarkable interferometer called the ALMA interferometer, also in northern Chile, but at a very high altitude, 5,000 meters, and it looks for gas and dust. Now, you know, most of you are familiar with dust. It's a blinking nuisance. But this dust is not the kind of dust that's behind your refrigerator. This is very small particles of silicon that are produced in supernova, exploding stars. And the heat from stars makes this dust glow. And so you can see this dust at early times, and you can measure how much starlight there must have been to produce these exploding stars. And you can get another age and pinpoint when cosmic dawn occurred. So again, Nicholas Laporte made this remarkable discovery of dust emission from another lensed galaxy at this redshift. And that tells us, again, that cosmic dawn we are approaching. So the future is very bright. Hubble, of course, is still operational, but there is a bigger telescope that's been completed, waiting to be launched, called the James Webb Space Telescope. The science case for this telescope has two big pillars. One is looking for exoplanets, and particularly terrestrial-like exoplanets, and the other is looking for the birth of galaxies. Due to be launched in 2021, so we're hoping very much to be able to use that to follow up our work. There are giant ground-based telescopes. These are very expensive. They're international, of course. They have to be. The Europeans are building one close to Paranal in the Atacama Desert. It's a 39-meter telescope. There are two American telescopes, the giant Magellan telescope and the 30-meter telescope destined for Mauna Kea. I was involved centrally in this project for many years when I was in Pasadena. If you look closely at this image, you can see it's not a single mirror. Keck itself is not a single mirror. It is what we call a segmented telescope. The mirror is 10 meters across, but it's made of 36 of these hexagonal segments. So imagine the engineering in making something like this work. TMT will have 492 of these segments, each one very carefully articulated as the telescope tracks across the sky. So these are enormous efforts. These are billion-dollar projects. The engineering alone is challenging. But, you know, as Fred Hoyle once said, a big telescope is an example of what our civilization does very well. So I want to end with an epilogue. Is all this worth it? You know, I told you we were looking for our origins. Astronomy, of course, doesn't really contribute very much to society in the technical sense, except through these ambitious projects. But it does inspire young people to get into stem cell subjects. So very recently there was a survey of 14-year-olds, and then they followed them through to university and onto all kinds of careers in science, engineering, mathematics, accountancy, and so forth. And they try to get them to understand what was the thing that inspired them when they were 12 or 14. And astronomy was one of the most frequent responses. So where better to end than with Hubble? So he was, apparently, according to people who worked with him, not a very good astronomer technically, but he was an extremely good expositor. And of course, he was living in Pasadena in California. He was very well connected with Hollywood. Here he is smoking. We're not allowed to smoke in observatories anymore. He wrote this book, which I urge you to read. You can get it on Amazon. It's been reprinted. It was originally published in 1932, called The Realm of the Nebula. And I think this sentence sums up why it's exciting to explore the universe. At the last dim horizon, we search for ghostly errors of observations. The search will continue. The urge is older than history. It is not satisfied, and it will not be oppressed. Fantastic words. Thank you very much.
Thank you very much, Richard, for a fascinating lecture. We have time for two questions.
Yep.
Yes, please.
Can I pass?
By of course.
I think I can be loud enough. We're recording.
Oh, right. Okay.
Okay, so this is an English major, question.
Okay.
What is the rest of space which is moving?
What is the rest of space? So we see all of space. We're, of course, living within it, and it is the entire universe is expanding, so space everywhere is stretching. So frequently I'm asked, you know, can I point in the direction of the Big Bang? And this is a misnomer because, you know, space is expanding in all directions equally. There have been ideas that somehow space might be expanding in one direction faster than the other, but to the extent that we've tested it from our observations, space is uniformly expanding in all directions. Space, space is indeed a thing. Yes, it does have properties. Firstly, it's, as you saw, it can be distorted, so by material. So it clearly interacts with material. So when the sun, you know, is blocked into space, space adjusts itself. And this was, of course, worked out by Einstein in 1918 and then verified in 1919 by this eclipse. Yeah.
Sorry, 1 second.
Thank you. Two quick questions, if I may.
Yeah.
Those early scientists that you mentioned, 1700, they discovered Milky Way.
Oh, so his name was Thomas Wright.
Yes. Did
Yeah.
they have any understanding that how far Milky Ways
No.
were?
No.
No.
He wasn't a scientist. He was a landscape gardener. He realized that this blur of light that he saw with the naked eye was due to the fact that the solar system was probably embedded within this disk of stars. And unfortunately, he didn't stop there, as I could have spent more time. He then changed his mind, and he thought the Milky Way was a shell. And you know, so he could have stopped, you know, after chapter 1, and it'd have been more famous. And then he put a supreme being at the center of the shell, and there are, you know, rather embarrassing pictures. But the book is, very, very interesting, and it is 1750. The key thing is he influenced the German philosopher Kant, Immanuel Kant. And Kant got the idea that if there was one Milky Way, there might be others. And Herschel, we don't know whether Herschel knew about Kant's conjecture. I don't think so. I think Herschel was very much an empirical observer, and he wondered whether there were other Milky Ways. And it was a debate. And you wouldn't believe it, until the 1920s, there were people willing to argue that the Andromeda spiral was inside the Milky Way. And you know, that's only less than 100 years ago, right?
Another quick question.
Yeah, sure.
The universe that you mentioned, 13.7 billion years old.
7 to 8 billion.
Yeah. Is it proven, or is it still theory?
We can measure the age of the universe several ways, and they agree. Firstly, we know a lower limit from the age of the oldest stars. We can measure the rate at which the universe expands and extrapolate back to a point. It's a little bit more complicated than that because the universe isn't expanding constantly. It's another story, but the universe is accelerating, as often knows, and so there's a correction you have to make for the fact that the expansion rate that we see today has not always been that same amount. And then finally, we can measure the age of the universe from measuring its constituents from satellites like the Planck satellite. And all these measurements have been refined. The most accurate age comes from the Planck satellite, and it's about 13.8 billion years. So for those of you who put that in context, the solar system is 4.6 billion years old. So the universe has been around for a lot longer than the solar system.
Thank you.
Since you just mentioned that the acceleration of the universe is the cost of the does it mean that the dark matter at the very early stage of the universe did not exist?
No. So the question was, since we observe the universe is accelerating, does that mean that dark matter had less influence at early times? Actually, it's the reverse. When the universe was very young, its history is governed largely by the amount of material, which leads to the question of what is causing the universe to accelerate. And it's nothing to do with the properties of dark matter, we don't think. It's a property of space that we don't understand. It seems that when the universe expands and reaches a certain density, the dark matter is no longer dominant in governing the slowing down. The universe is originally slowing down, and as the universe expands, the role of the dark matter gets less important, and then whatever causes the acceleration kicks in. And there are papers every week on what is the origin of this accelerating universe. And the plain answer is we don't know. We don't know what is causing. It's one of the biggest mysteries in cosmology to cause the acceleration of the universe. And indeed, our parent professor here loses many sleepless nights worrying about exactly this problem.
If the Big Bang happened at like a point, and then you said it's been expanding uniformly everywhere,
Yeah.
then why does it not look like very uniform now?
Why doesn't it look like?
Why doesn't it look very uniform now? Why is there so much variety if it's just been expanding uniformly?
Well, we see structure. So when the universe expands, as you're right, the density goes down. But there are seeds of growth that we see in the glow from the Big Bang. The Big Bang, and this was a huge adventure, when the Big Bang was detected, everybody knew that the universe should be smooth at some level at that early time, but there would be lumps and bumps in it. Otherwise, we wouldn't be here. How could we be here if there wasn't structure? And it took 25 years to find that structure in the 1990s, and it was another Nobel Prize when we start seeing the structure in that Big Bang, and in the glow from the Big Bang. And the reason that structure is there is it relates to the earlier question, and that is that dark matter is not the stuff that makes up you and me, and it fractionates out of the expansion of the universe even earlier than the hydrogen atom. And it's got its own mass, so it has its own gravitational pull, so that if you like, there are dark matter nuggets sitting there that cause these ripples and bubbles in the microwave background. And then when the hydrogen forms, that hydrogen is drawn to that dark matter, those dark matter nuggets. And so if there wasn't dark matter, we wouldn't be here, because we are sitting, the Milky Way is sitting in an enormous lump of dark matter that's like a halo around it. And so that structure is accelerated by the growth of dark matter. Why? Well, the dark matter separates out from the expansion of the universe very, very early, and it's quite heavy, and so it has its own gravitational, it's attracted to itself. And so it creates these lumps of dark matter very early on. And these, what we call instabilities, create structures that later develop, that lead us to galaxies. So these fluctuations in the early universe are very, very important, understanding where they come from. But they have to be there, otherwise we wouldn't have, we wouldn't be here today. As you say, the universe would then be completely smooth.
Richard, you mentioned the wonderful results of Hubble Space Telescope.
Yep.
For many years, the next big thing is
James Webb. Yeah.
telescope.
Yeah.
What's your own dream?
So I think we're,
What's the one thing you
final
want to
word,
see?
because I think the
Final
clock is running on, but I think, this cosmic dawn, finding these early objects, statistically, I think, we may find one or two weird objects that have no chemical elements, but I don't think that will be the proof. I think demonstrating that we can measure the ages of these objects and hence see this early burst of star formation in these early objects. That is within scope. As we said in our Nature paper earlier this year, that is within reach of the James Webb Space Telescope. So hopefully, 3 or 4 years to wait before that very nice discovery.
Very good. I think it's the first lunchtime hour within 50 minutes. The speaker managed to cover 13.8. So I think let us think.
Thank you. Thanks very much.